Hello, everyone.
Hello, good morning.
Good morning.
Can you hear me?
Good morning.
Yes.
Nice to have you all here. I think just one moment and then we will start. It's nice to have you all here. This is FASTCH2ANGE second workshop, and will be aimed to foster networking and feedbacks and comments from different projects that are working on the same topic. And all the projects that are involved in today's meeting are from Clean Hydrogen Partnership. And so I think I will start by sharing my screen with a 3-minute video about the Clean Hydrogen Partnership, so we can give good visibility to the clean hydrogen. 1 second. Then we will start.
The EU has set itself the ambition to become the first climate neutral continent in the world. And of course, hydrogen will play a crucial role to meet Europe's climate ambitions. And the EU is supporting the hydrogen economy to be moving from a niche economy to scale.
The Clean Hydrogen Partnership is working really hard to addressing two main challenges: skills and knowledge management. For skills, did you know that by 2030, over 1 million people will be employed by the hydrogen value chain? And this number will be 5 times bigger by 2050. So for that, we need to educate young students. We need to upskill existing workers.
The Clean Hydrogen Partnership, after bringing several solutions, technological solutions into the market, has become innovative, creative in terms of business models. So came with the idea of the hydrogen valleys, and hydrogen valleys, by definition, are putting together the production and the use of hydrogen, solving somehow the chicken and egg problem, as we call it. We will bring the hydrogen economy locally and successfully to the people.
Hydrogen will play an inevitable role in the green transition era, and because we cannot combat the climate change without hydrogen. And to what extent and when it will become a mature technology is the only open question. Is not if.
The thing what we have done with Baltic Sea Hydrogen Project is that we have brought together a large group of companies from different sectors, and these companies cover the entire value chain needed for clean hydrogen or the hydrogen economy to be established.
The Clean Hydrogen Partnership plays a very important role to support existing hydrogen projects to become commercially viable. And that's what we need in the European Union. We need to scale up and we need to start commercializing hydrogen on our European markets.
So thank you all for being here. I must present myself, I think. I'm Angelo Medui. I'm a chemist. I work at RINA, and I'm the coordinator of FASTCH2ANGE project. And as other projects involved this morning in this workshop, this project is a clean hydrogen project. but it is also about a common theme that most of the projects of today are, some of the projects at least, which is the fuel cells and the problem, the issue of PFAS compounds. The other projects, the project that will be presented today are Promisers, ECOPEM, SUSTAINCELL, AEMELIA, Everywh2ere. And together with us, we also have the head of the advisory board from FASTCH2ANGE, Dr. Matteo Tellaida, and also one member of the advisory board should be present, Professor Isabella Nicotea from University of Calabria, who is here. She is an expert in membranes and in these specific topics that we will talk today. So we hope to have insights and comments and feedback. We are glad and happy to have her here. I think we can start with the presentation of the first project. And the first project is Promisers, which will be presented by Dr. Sandra Martinez-Crespiera. She holds a PhD in chemistry from Universitat Autónoma de Barcelona and a postdoc from TU Darmstadt. And since 2013, she is developing a professional career in the area of advanced materials of the R&D department of LATAT Technological Center, leading the group of nanomaterials with the main interests being the development of inorganic and carbon-based nanomaterials and catalysts for energy applications such as storage, conversion, and harvesting. She has participated in various conferences, workshops, seminars, and has publications in international journals. So please, Dr. Martinez-Crespiera, the word is there. You can start your presentation. Thank you.
Thank you very much. Can you hear me?
Yes.
Okay. Thank you very much for your nice presentation. I have a problem because I cannot share. There is blocked the shared option for my presentation.
Check now. Please.
Now. Okay. Yes. Now it's.
Thank you.
It's possible. Okay, so I hope you can see my screen. Okay,
yes.
Thank you. Okay, so as Angelo said, so today I'm going to present the Promiser project. It is a project about the substitution of pair and polyfluoroalkyne substances, polymers in electrochemical systems, in this case, proton exchange membranes, fuel cells and electrolyzers. This is a project that is coordinated by Marcel Boerrichter. Today he is not here because he couldn't attend, and I'm going to do my best to present it. Okay, so as you know, the problems with the PFAS is that they are very stable, and therefore they can be accumulated in the environment and also in our bodies, and are responsible of healthy issues and also problems with the environment. Therefore, we need to substitute this kind of substances. And we know that they are very commonly used in electrochemical systems and, for instance, in fuel cells and electrolyzers. And therefore, this is how Promiser's project is born. Is a project to substitute these PFAS-based polymers in proton exchange membrane fuel cells and electrolyzers. It is a project inside the call of Horizon Europe and the Clean Hydrogen Partnership that started last year, January, a total budget up to 3 million and a duration of 3 years. These are the different partners of the project. So it's basically based on 4 major companies: Syensqo in France, Humatech in Germany, Industrie de Nora in Italy, and Rina Consulting in Italy, 2 SMEs, Selfion in Sweden, HyCitech in Italy, and 3 technological centers, LATAT in Spain, TNO in the Netherlands, and IIT in Italy. The project is based on this non-fluorinated ionomers development that will be used for the manufacturing of the membranes and also the different electrode inks and the corresponding MEAs. And for that, we focus on two different types of ionomers, hydrocarbon-based ionomers and bio-based ionomers, and basically nanocellulose-based ionomers. So what we target is chemical stability up to 2 volts and ion exchange capacity higher than 1 millimole gram, and an in-plane ionic conductivity higher than 250 millisiemens centimeter. From these ionomers, we will get the two different types of membranes with resistance for fuel cells at the level of lower than 0.03 ohms square centimeters or 0.08 ohm centimeters in the case of electrolyzers. We target also a swelling lower than 30%, tensile, good mechanical properties with tensile strength higher than 40 megapascals, and a gas barrier crossover current density lower than 0.5 milliampere square centimeter. For the ink, we also target that is stable at least for 4 hours, that is homogeneous when we deposit. And it's true that we don't focus on the catalyst. We will use commercially available platinum and iridium-based catalyst, but we target using less than 10% of this catalyst in the electrode ink. Then these membranes and electrodes will be assembled in a MEA, and afterwards we will validate in a single cell and in a short stack with dimensions of 25 square centimeter and up to 5-10 cells per stack. In the case of the fuel cell, with a degradation rate lower than 5 microvolt hour at these conditions, and in the case of the electrolyzer, a degradation rate also in the same level at these other conditions. Then we also focus on modeling studies in order to optimize the design of this MEA and the corresponding cell and stacks. And we also want to secure the sustainability. And apart from focusing on these non-PFAS containing ionomers, also to focus on renewable and non-toxic solvents for the production of these inks and membranes, also sustainable components, upscalable sustainable manufacturing processes, and we will do also this life cycle analysis and life cycle cost in order to reduce down to 20%, up to 20% environmental impact of the different systems. So this is the schema of the project. So we go from TRL2 up to TRL5, from the materials development to the final electrochemical systems, and focusing on these two ways, hydrocarbon-based ionomers and bio-based ionomers. So the first two work packages are focused on this material development, ionomers and membranes, and in formulation. The second, the third and the fourth work packages are more focused on the cell design and the modeling, including also operanding techniques. And in the final, in the work package 5, we focus on the stack for the fuel cell and the electrolyzer, including also the modeling and operando techniques. And finally, the work package 6 and 7, that is transversal, and we focus these safe by design principles. So this is more or less how the work packages are distributed. So, and we have these 5 work packages dedicated to the synthesis and development of the ionomers, membranes, electrode inks, MEAs, and the different stacks, cells and stacks. So I will go briefly on the development of this work package. For the first one, in which we develop hydrocarbon-based ionomers. So now we are developing different type of hydrocarbons, and we have reached the ion exchange capacity up more than 2 millimole gram with ionic conductivity higher than 220 millisiemens centimeter, and with mechanical properties also very promising. And we also focus on different polybenzimidazole polymers because they provide excellent thermal and mechanical properties. We can also have different number of terminal functional groups in order to cross-link this membrane and to have better mechanical properties. And also they can provide us with cavities like mesoporosity to favor the absorption of the phosphoric acid. Regarding the membranes for this hydrocarbon-based route, we are testing now the casting of this ionomer, and we are producing the first membranes at lab scale, but the next step is to upscale this production and also to substitute the organic solvents that are used nowadays for more greener solvents. Also, we want to reinforce these membranes by means of nanofiber non-woven mats that we produce by electrospinning. I don't know if you are familiar with this technique, but this technique is dependent on the polymeric solution properties, like the molecular weight of the polymer, the concentration, the solution conductivity, and the surface tension, the main ones. And we can control also the electrospinning conditions, like the flow of the polymer solution, the voltage, and we are controlling also the distance to collector. And by these different parameters, we have managed to electrospan different types of polymers like polysulfones and polyamides, as you see in the images. And now we are working on the post-treatment of these mats in order to cross-link thermally or chemically in order to be more stable with the different solvents that are used for the membrane manufacturing. And therefore, we have managed to cross-link the polyamide nanofiber mats that they can resist DMSO and also dimethylacetamide solvents. And another way that we are exploring is also to substitute the solvents we use for the electrospinning for more sustainable solvents to accomplish the safe by design principle. Regarding the bio-based route, we are working with nanocellulose, and in order to enhance this ion exchange capacity, we are working on the surface functionalization of this nanocellulose. We work with both types of nanocellulose, crystalline 1, CNC, and fibrillar 1, CNF. For the crystalline, we are proceeding with sulfonation in order to include these sulfonic groups with negative charges that will favor the proton conductivity. And we have managed to reach this functionalization up to 3% of sulfur. That means a degree of substitution of 0.17 of this nanocellulose. For these bio-based membranes, Cellfion is working with the CNF, with the combination of the nanofibrils, modified nanofibrils, with sulfonated polymers like polysulfanes or lignosulfonates, in order to enhance this ionic conductivity, no? And they are measuring the different properties. And the process to obtain these membranes is by filtration or coating techniques, a drying process with or without vacuum. And also they do these post-treatment steps such cross-linking or annealing. So you can see in the image some of these nanocellulose-based membranes that here they are transparent. Also, we are working on the reinforcement of these membranes using nanofiber non-woven mats by means of electrospinning process. And now we are working with cellulose acetate polymers to obtain these mats, and with the functionalization of these nanofibers with different surface modification or particle incorporation, like metal oxide and organic particles, in order to increase the mechanical properties and the ionic conductivity. The next step is the ink formulation with these ionomers and subsequently development. So we are working on the preparation of these inks and the application by direct coating and slot die coating. We have already selected different types of PTLs for this MEA development, and we are performing this manufacturing of the MEA. And in the last step, we started the modeling of the different membranes in order to assess on the membrane transport phenomena to study the transient numerical model to predict the water concentration, the temperature, the potential, and the pressure. We are also working on the application of sustainable by design framework by the hazard assessment of chemicals and materials, the human health and safety aspects in production and processing phase, and the human health and environmental aspects in the final application phase. We also work with operando techniques like Raman, infrared, XPS, SEM, and TEM to better understand the problems and the issues happening inside the MEA. And in the final step, we will construct and manufacture the different stacks and the different electrolyzers and fuel cells. And that's all of my presentation. Thank you very much for your attention. If you have any question.
Thank you. Is there any question from the audience online or here? Oh, yeah, there is one question from Andrea Rosati online. Please, Andrea.
Thank you, Angelo. Hi, Sandra. I'm Andrea Rosati from RINA CSM. I want to know, this is just a curiosity. I have seen in your slide that you code a technique direct coding for the deposition. What means exactly direct coding? Use a barcoding application or what else? Just a curiosity.
Okay. Yeah, this is something that we are not doing. So yeah, probably I would better ask my colleagues because I cannot answer from their name because it's their process. So if you send me an email, I can forward to them and yeah, they can better answer you because I don't want to say something that I am not sure. Sorry.
Okay. Okay, no, you're welcome. And another question is relating to the aging solution. So if you test your material with aging solution, if it was made a difference between the aging solution of proton exchange membrane full cell and you use another aging solution for proton exchange membrane electrolyzer. So if you use different aging solution for these two, for simulate the environment of these two devices or
okay, the same as I mentioned before. I think it's better, sorry, because I am not doing these experiments and it's better that you write me an email and I will forward to my colleagues just to
okay. Okay. Thank you so much. Thank you.
You're welcome.
Yeah, another question from one of the other speakers of today, Dr. Frederic Onana.
Yes, hello, could you hear me?
Yes.
Yes.
Okay, yes, thank you for the nice presentation. I had two questions. The first question is related to PEM water electrolysis application. So the common practice for those membrane is to have some recombination catalyst inside of the membrane. And my question is, did you experience some trials with some catalyst inside of the membrane, and what was the result in terms of gas permeation? That's the first question. And the second question is related to the membrane degradation. So let's say the phantom process is a common way to assess the chemical stability of the membrane. And I wanted to know if you perform such kind of test with your hydrocarbonate membrane.
Okay. Yeah. I am not working on that membrane issue. I know that what I show you today, and therefore, yeah, I said the same I said before, sorry, because yeah, I'm more focused on the nanocellulose functionalization, and therefore I cannot answer that. But as I said before, please send an email to me. I don't know if you know my email, and I will forward to my colleagues, please. And sorry.
Okay, thanks.
Mm-hmm.
So very nice work, by the way. And I have a curiosity, since you work on nanocellulose, can I ask, maybe you mentioned it, I missed it, the source, the source of the cellulose, if you know it.
Yes, it is wood. It is from wood.
Okay.
The one that we use in Leitat is commercial, so we don't extract nanocellulose, but the one produced from Selfion, they produce it themselves and is from wood.
So at the end, you want to close the circle because you are testing it with commercial one, but in the end, you are foreseeing in the future to use the one produced internally. Okay, perfect.
Yes. Yeah. Okay, thank you.
We have a question or a feedback from Matteo.
No, it's just a question. Hello. Very nice presentation. Congratulations. And it was my question was related to the cellulose. You said that this is provided by Selfion, and so did you say that is that a nanocellulose degree materials in first place, and in the second place, I was wondering about the functionalization. How do you, what's the extent of the functionalization? I mean, do you expect to permeate and to go deeper in the cellulose while you are functionalizing it? And did you expect to, I don't know, to have a degree of functionalization that is correlated to the efficiency of the membranes containing those kind of materials? Is there a correlation with that?
Yeah, this is an issue because it's true that the nanocellulose itself tends to agglomerate and the surface is difficult to access. Therefore, we are always limited with the degree of substitution up to 0.304. No, this is the main issue. Therefore, Selfion is also working with this compounding with the polymers, with the sulfate groups. And I think this will be the approach. So we will try to maximize this surface functionalization, but we are limited. Therefore, we also work with crystalline nanocellulose because the surface is more reachable and we can better put these functional groups. And we will combine with the CNF and then also with sulfonated polymers.
Okay. Thank you very much.
You're welcome.
If there are no other questions for Dr. Martinez, then let's thank her for the speech of today. And,
thank you very much for your invitation.
Thank you for being here, and hope for you to stay around to make questions to the others as much as they did with you. So I think we can move on with the next project, which is ECOPEM, and ECOPEM will be presented by two speakers, Mohamed Iksan and Matthias Resever. Mohamed Iksan holds a PhD in energy engineering from the University of Science and Technology, Korea, specializing in ion-conducting polymer membranes for water electrolysis and redox flow batteries. He is a postdoctoral researcher Forschungszentrum Jülich, and the other presenter will be also for the same project, Matthias Resever. He holds a master's degree from ENSMAC in Bordeaux. He's specialized in energy storage and conversion, hydrogen fuel cells, electrolyser, batteries, and photovoltaic panels. Since 2023, he has been working at Symbio as MEA, material designer for hydrogen fuel cell. So please, Maya and Matthias. I think you're muted. Oh, okay. Yeah. Hello, Maya. Hello, Dr.
Hello.
Issa. Hello.
Yeah, I'm sorry. I think I have a problem with my computer at the moment. Could you give me 5 minutes, please?
Yes.
Yeah, thank you.
We can.
Maybe I can start with
Yeah,
my
maybe
presentation in between,
yes.
if
Yeah.
you could be there. All right. Can you hear me correctly?
Yes.
Awesome. All right, can you see my screen?
Yes.
Excellent. So, thank you everybody to welcoming us as a campaign project. Where I'm going to present especially the part of Symbio in this project. And briefly to present it, we are developing non-fluorinated components for PEM fuel cells and electrolyzers. Basically, we want to create an object, at least a short stack, which is fully based on hydrocarbon technology, from reinforcement to even trying the GDLs and everything in the fuel cells and electrolyzers. So briefly, I'm going to be very short because I know Maha is going to present in his next presentation. But here are the main work packages in the project. So basically, work package 2 aims to develop ionomers and membrane, which are fully hydrocarbonated. Work package 3 is mostly focused on the development of the reinforcement for these membranes that were made by the University of Birmingham. Work package 3 is led by Aaron in Germany and Yulish as well. And for work package 5 and work package 4, we aim to create different catalyst layers. For work package 5, it would be for the goal of the fuel cells. And for work package, for package 4 would be for the fuel cells, and work package 5 for the electrolyzers. And Symbio works especially in work package 6, which is the sum up, we could say, of every previous work package. So the idea for this work package is to create some short stack and to test them. Like you mentioned in the previous project, see free close, but we want to test them electrochemically to see the performances and the durability. And we will test it at single cell scale and at lab scale, and also at short stack in our facilities at Symbio in France. As a transition, just a simple slide to explain a little bit what company is Symbio. So we have 3 shareholders right now, and we focus mostly on developing stacks for the automotive industry. I think Symbio has been created in the 2010, and started as a startup, obviously, but grew up pretty quickly this last 5 years, I would say. And we have since 2 to 3 years a gigafactory here in Lyon, in France, which you can see at the bottom left of the slide, which is made to develop all these stacks we want to produce. If I want to go more into the details, so the goal of the work package 6 that is supported by Symbio is to scale up the processes that were defined in the previous work packages, so the formulation, the coating, the MEA assembly. And the idea is to develop all this technology for a large-scale MEA at 200 centimeters square. And in the end, we want to create 2 short stacks of 10 cells each. In order to test them afterwards. You can see at the bottom right of the slide the performance we want to target. For the KPI for the fuel cell, we want to target 1.5 watt per centimeter square at 0.65 volts. So that's the power that was targeted for the project. And we want to avoid a degradation rate above 5 microvolts per hour for the testing of these fuel cells. This is quite challenging because these are new materials and completely developed from scratch. And so we are actively working together as one group to develop these
these materials and validate these performances. So just to go further into the steps of this work package, Symbio aims to develop large-scale MES, so that's why we need to first make a large-scale ink formulation. And here at Symbio, we have enough material and prototypes device to produce these kind of things. So you can see here a formulation of a 2-liter ink in a mixing tank, and the idea is to do that for these projects with completely PFAS-free ink formulations. And in the end, testing them in rheology, granulometry to see the particle size distribution, for example, to see the catalyst layer, how they behave, and how the ink is dispersed. Also, we want to make some SEM measurements, and in the end, the idea would be to coat these inks on hydrocarbon membranes that would have been developed in Work Package 2 and Work Package 3. The idea in the end, as I told you, would be to develop 10-cell short stack, 2 of them with 200 centimeter square cells. And for that, we just want to make sure we have enough. So we're going to produce at least 3 large area CCM in our facilities. Furthermore, we will work on the assembly of the stacks, obviously, and we're going to select some GDLs of gaskets, gaskets and bipolar plates, to make sure that we can produce these 10-cell short stack. And in the end, for the characterization of the stack, we're going to work with EPFL, because one stack will be used for higher temperature in our facilities in order to reproduce the conditions that would be used in heavy-duty vehicles. And another stack will be reproduced in order to compare it to a PFAS-based solution at EPFL, so it's Switzerland, in Lausanne, specifically. And we'll conduct some different electrochemical techniques that I think you're familiar with. And so the idea would be to test all of these stacks on the short stack we can show you now, and to reach the targets at the end of the project. So thank you so much for hearing me. Here are the list of the contributors and the collaborators for the project ECOPEM. And if you have any questions, don't hesitate to ask. Thank you.
Thank you, Matthias. If Dr. Iksan is ready, we can keep on with him, and the question will be at the end. Otherwise,
yeah.
Okay.
Mm-hmm. So yeah, can you see my screen?
Yes.
Great. So thank you very much for the introduction. I'm sorry for the technical problems.
Oh.
So yeah, I think Matthias already gave some brief introduction about the ECOPEM project. It's a project part of the Horizon Clean Hydrogen project in the topic of development of non-fluorinated components for fuel cells and electrolyzers. So this project itself was started this year on the 1st of April with a total budget of 4 million euro. And we have here in this ECOPEM project 7 partners that are collaborating together. In the academic field, we have University of Birmingham, EPFL, and also with the SES. Also for the Research Institute, we are part of Forschungszentrum Jülich. And also there is Hirion in Germany and IFE. And for the industry, Symbio, who just presented part of his work package, is also part of the project. So starting from the background itself, we know that Nafion or Aquifion is part of perfluorinated sulfonic acid membranes and ionomers that currently used in PEM fuel cells and electrolyzers. But unfortunately, this type of perfluorinated chemistry can be considered as a 44 chemistry because it's not really easy to BDK in any types of solvents that we have, and it poses a serious danger in environmental conditions and also serious health concerns because of this release fluorine groups. And depending also in the type of Nafion that we use, depending on the thickness, it is also quite costly, and we can expect that if we want to have around 1 kilowatt of PEM water electrolyzer, it will cost us around $20 per kilowatt per 1 square centimeters PEM water electrolyzers. Therefore, we need a great substitution for this PFAS material, which is more friendly and more durable, and it is based on the hydrocarbon-based polymers for both membrane and ionomers, because these hydrocarbon-based polymers can be easily recycled because of their solubility in available organic solvents that we have, or maybe non-organic solvents like based on water-based solvents. And also, according to the GERK models, Nafion has hydrophilic channels between 1 to 4 nanometers. That's why the hydrogen crossover is relatively much higher than that of hydrocarbon-based polymer, which has lower hydrophilic domains, lower channel size of hydrophilic domains. That's why we expect that by using hydrocarbon-based polymers, both membranes and ionomers, we can have a much lower hydrogen crossover, and also leading to a lower degradation from the formation of radicals because of hydrogen crossover. And also we expect that by using hydrocarbon-based polymers, we can operate the fuel cells at a higher temperature, around 100 and 120 degrees Celsius, simply to reduce the device to remove the heat to simplify the operation of fuel cell. I think Matthias explained this already about our target. For the fuel cell itself, we are targeting the operation at 1.5 watt per square centimeters at 0.65 volts. And for the water electrolyzer, we are aiming for the performance at 3 amps per square centimeters at 1.8 volts, with the degradation rate of 5 microvolt per hour. And as I mentioned before, we try to use hydrocarbon-based materials for both ionomers and membranes. So basically non-fluorinated in both polymers. And also for the application, we are aiming to perform 10 cell stacks for both fuel cells and water electrolyzers. Matthias explained this already about the work package, but today I would like to focus on these two, work package 2 and work package 3 and 5. Work package 2 is the development of non-fluorinated ionomers and membranes that is currently done by University of Birmingham. And for the ULIC itself, we are developing the non-fluorinated reinforcements and also the testing in water electrolyzers. And for work package 3, which is the development of fibers, we are using a non-fluorinated polymers and ionomers to make a nanofiber mesh to support the membrane. The idea is to mechanically reinforce the membrane, but at the same time, the reinforcement should give low to zero reduction in proton conductivity. And we use this electrospinning techniques to produce the nanofibers for the reinforcement later. So the objective itself for the production of the reinforcement, we are targeting to use sulfonated hydrocarbon-based polymers by using non-toxic solvents. And at the moment, we are still using the MSO. These polymers should be suitable for electrospinning, because we know the electrospinning is really much depending on the conductivity of the polymers and also the conductivity of the solvents and also the humidity and the temperature. And we know that sulfonated hydrocarbon base itself sometimes has high water uptake, and it will lead to unstable materials during the operation if it absorbs a lot of water. So we try to adjust the IEC by doing acid-based blend to introduce ion pair interactions. By doing so, we can improve the mechanical properties, and also we can cross-link the material by using this ionic cross-linking between the sulfonated polymers and the basic polymers. And in this case, for the first trial, we use the known sulfonated polyether sulfone with the IEC of 1.8 milliequivalent per grams. And we do the acid-based blend technique with the polybenzimidazole. And in this case, we use OPBI with ether connection between two phenyl rings. And we try to make a several blend ratio to get a suitable fibers that can reinforce the membrane later when we have the membranes from the University of Birmingham. And from one of the ratio that we did, we could produce the nanofiber mats with quite homogeneous diameters of the fibers. And we did pore filling by using Dr. blade coating. And we got a membrane with a thickness around 44 micrometers. And as you can see here from the slide, you can see still there are still some pores in the pore-filled membranes, because this membrane is not being hot pressed yet. So if we hot press the membrane above the glass transition temperatures of the membrane, then we can easily remove the bubbles or the airs between the fibers. I think that's all from my side. If you have any questions.
Thank you, Dr. Iksen. Is there any question for his presentation or also for Dr. Everywh2ere presentation? Yes, we have a question from Dr. Martinez.
Thank you. Very nice presentation. Thank you. I have a question for this last comment that you focus on electrospinning and more sustainable solvents. You mentioned the MSO. Did you try any other more sustainable solvent for the electrospinning, or which solvents you have in mind?
There is one solvent that I have in mind. It's based on ethanol KOH mixture. So we can tune the solubility of polybenzimidazole and sulfonated polyether sulfone in 2% ethanol KOH mixture. But unfortunately, we are still a bit confused with this behavior of solvents, because we put KOH inside, and the collectors in the electrospinner is based on aluminum foil. And if aluminium makes contact with the KOH, it can produce hydrogen. So at the moment, we are still struggling with this solvent besides DMSO, but so far the most suitable solvent for these types of polymers is DMSO.
Okay, thank you.
Any other question? Yes, we have Dr. Nemet, another speaker from today.
Thank you very much for the nice talk. Yes, I would have a connecting question to the previous one. So basically, you mentioned that if you develop this KOH alcohol mixture as an alternative solvent to dissolve this OPBI based blend. But if you use KOH, then you deprotonate the sulfonic acid group and also partially the MPBI or OPBI. How would you form then the acid-based blend? Because there is no proton left.
The acid-based blend can be done later for post-processing. So the moment we have the fibers, we can immerse that in acid solutions to remove the potassium form of the sulfonic acid, and we can reprotonate the polybenzimidazole into imidazolium. Therefore, we can have ionic interaction later. And to enhance more the ionic interaction, we can do post-processing again by heating up the fibers above 180, for example, just to speed up the kinetic of the ionic cross-linking.
Thank you for the answer.
Yeah.
Is there any other comment, feedback? Otherwise, let's thank both the speakers, Dr. Iksan and Dr. Everywh2ere. And it was nice to have you here. And also in your case, I ask you to stay for asking questions to the other speakers. Now we can move on to the third project of today, which is SUSTAINCELL. And the speaker is Dr. Tamas Nemet. Dr. Tamas Nemet holds a PhD in chemistry with a focus on supramolecular chemistry. He spent 2 years as a postdoc researcher at ETH Zurich, where he developed novel compounds for magnetic resonance imaging. He then joined the Paul Scherrer Institute as a researcher to work for 4 years on the development of fluorine-free membranes for low-temperature fuel cell and electrolysers. For the past 2 years, Tamas has been a research scientist at SINTEF, one of Europe's largest independent research organizations. And today he is here to represent the SUSTAINCELL project. Please.
Thank you very much for the kind invitation and introduction. I hope the slides are visible in full screen mode and you can also see the pointer. Perfect. Yes, so SUSTAINCELL, it is an abbreviation of Durable and Sustainable Components Supply Chain for High-Performance Fuel Cells and Electrolysers. I'm presenting here on behalf of the project coordinator, Marie-Laure Fontaine, senior researcher and chief scientist at SINTEF. But of course, several other partners are involved, which I will name on the next slides. So this project is coordinated by SINTEF from Norway. Apart from that, we have several partners from France, CNRS, University of Montpellier, CEA. We have also partners from Germany, such as Forschungszentrum Jülich and also DLR. Then we also have partners from Denmark, DTU, then from Spain, Tecnalia, VTT from Finland, and also 2 partners from Switzerland, EPFL and AGS. So 9 of these partners are full partners, and the 2 at the end, they are associated partners. Yes, basically in the SUSTAINCELL project, we aim to develop novel technologies to make the European supply chain sustainable. And so this flow chart here shows all our approaches. Basically, we are looking into materials with reduced amounts of critical raw materials. So by that, we mean to develop new alternative materials and also recycle existing raw materials. And apart from that, we aim to design and prepare new components and cell architectures where we drastically reduce the CRM content. We also aim to integrate these recycled and optimized processes into the work stream. And also we validate the performance and durability of the new components and materials and benchmark them against state-of-the-art technologies. And apart from that, we also disassemble after testing both the devices and the components. Therefore, we can recover like at high rates the different components and reuse them after successive treatment. And by this, we can define and optimize processes for conversion of recovered materials to new sustainable feedstocks. And by doing so, we are focusing on the energy sector, so next generation electrolyzer and fuel cell technologies. This includes both low and high temperature applications. So the project is a 6-year project. It started at the beginning of 2023 and lasts until 2028. The total budget is 10 million euros. And the SUSTAINCELL project, of course, greatly appreciates the Clean Hydrogen Partnership and the European Union for funding. So our aims is to prepare the European supply chain for the fuel cell and electrolyzer technologies. And in this case, Europe is heavily reliant on external manufacturers. And our aim is to basically develop a pull effect by the end of the project and also beyond the project results, and somehow decrease our reliance on external partners, be it in China, Asia, or other continents or countries. So basically, we are focusing on the full material supply chain, be it raw materials. So here are some examples. Also processed materials such as PFSA and non-PFSA based polymers that we have heard about in the previous 2 presentations. And also when we integrate these raw materials and processed materials into components such as the membrane electrode assembly or then further advance them and make electrolyzers and fuel cells. Yes, and I would like to also show the technologies that we are focusing on in more details. So on the left side, we have the electrolyzer technologies, and on the right side, we have the fuel cell technologies. So both for energy storage and use devices. So we are focusing on both low temperature and high temperature applications. So our innovative approaches involve alkaline electrolyzer, proton exchange membrane electrolyzer, and anion exchange membrane electrolyzers, and also solid oxide electrolyzer technologies. And besides that, we are also focusing on proton and anion exchange membrane fuel cells and proton conductive ceramic electrolyzers as well. Yes, and of course, in the beginning of the project and already during the proposal drafting, we identified key performance indicators that the SUSTAINCELL project aims to reach and also surpass. Here is a general overview of them. I won't name all of them by detail, but just a few examples. So in case of platinum recycled after use, the SRIA targets by 2030 99% weight percent recovery. So this is a very ambitious target that we are also trying to reach. Then we also have similar aims as the previous 2 projects for electrolyzer or fuel cell performance and durability as well. And also some key economic indicators such as the capital expenditure dependent on a respective technology. Yes. Next, I would like to show some preliminary results that were used in the proposal writing. So for example, at CNRS, in the groups of Frederick Yowen and Deborah Jones, they developed a solvent-free synthesis method for fabricating platinum group metal-free catalysts that can be used for anion exchange membrane fuel cells. So here is the general overview of that. So these novel catalysts are nickel based that are also comprising of a nitrogen doped carbon overlayer. So here is an overview of the targeted activity for the hydrogen oxidation reaction of these new catalysts. Also then at Highern, in the group of Johan Kerres, fluorine-free blend membranes are being fabricated to be used for anion exchange membrane water electrolyzers. Here is the general structure of that material and also the targeted performance. And also a real photo of an already made membrane. So these membranes are based on piperidinium as anion exchange groups. Besides that, here at SINTEF, the group led by Marie-Laure Fontaine developed new electrodes that can be used in proton ceramic electrolyzers. So they are based on these metals. And here is the full fabrication process to make the porous electrodes and some images at various temperatures. So since the project started in 2023, we already have some early results. Namely 5 publications and also 1 book chapter, but of course there is many more in the pipeline. So it's typical for such long projects that most of the results are being published at the late stage of the project. But we already are proud to have some results from the respective partners, so such as Highern, EPFL, AGS, then also Highern in combination with DTU, and also Highern with SINTEF, and also separately DTU and CNRS. Next, I would like to focus on one use case of a recently published result, namely where we develop fluorine-lean phosphonated polymers of intrinsic microporosity with high oxygen permeability to be used in proton exchange membrane fuel cells. So here I would like to give a broader context why we are doing this. So we all know the challenges of global warming, air pollution, and energy security. And here energy storage and conversion devices can be used to mitigate the detrimental effects of climate change. So if you look at the pie chart of greenhouse gas emissions in Norway, then we realize that 24% comes from the transportation sector. For Europe and for other developed countries, this metric is even higher, so it's 33% even. So something needs to be done, and integrating fuel cells into the transportation sector is a possible solution to this. And fuel cell is one of the green technologies that are being advanced. And here is a 3D blender image of the specific fuel cells that we are using here at SINTEF to test the new materials. And the use case I would like to highlight now is for proton exchange membrane fuel cells. So we all know the respective anode and cathode side reactions for hydrogen oxidation and oxygen reduction to produce electricity. So the heart of this device is the proton exchange membrane, which is sandwiched between catalyst layers. Currently, the limits for market penetration of the fuel cell technology is the high price of the membrane electrode assembly. And this is also related to the polymer chemistry that is used in the catalyst layer and in the proton exchange membrane, because these devices are still based on PFAS. And for the energy sector, we use PFSA as a subgroup of PFAS. Our aim here was to develop new fluorine-free polymers that can be used as a catalyst layer ionomer binder and also as a proton exchange membrane. We have to differentiate between the two. So an ideal binder in the catalyst layer has good electron conductivity, effective proton and gas transport. But as a proton exchange membrane, we expect it to have high proton transport, but it should act as an electric insulator and also as a gas barrier. So it is somehow cumbersome to use the same polymer for these two applications. But this was our ambitious goal to reach it. So we all know the benefits of PFSA or PFAS. They have excellent performance, durability, and the balanced gas permeability that makes them ideal materials as a catalyst layer binder and as a proton exchange membrane. On the other hand, if we replace PFSA in the membrane electrode assembly with aromatic hydrocarbon polymers, these alternative materials are expensive. They can have a high and comparable performance to PFAS. They have vastly improved durability and also low gas permeability, which makes them ideal as a proton exchange membrane. However, due to the low gas permeability, they are not ideal as a catalyst layer ionomer. So there is a need to change the chemistry of these materials to improve performance when used in the catalyst layer. So a new family of polymers called polymers of intrinsic microporosity aims to solve this issue by creating such a structure where high oxygen diffusivity is possible. Therefore, these materials are especially attractive to be used as a binder in the catalyst layer. So the group of Johan Keres at HYERN synthesized this polymer, and this polymer was tested at the SINTEF, and we integrated it into the membrane electrode assembly to reach high fuel cell performance. Apart from that, fluorine-lean polymers have been synthesized at HYERN that can be applied both as a binder material and as a proton exchange membrane. So this is the structure that has been synthesized. So the material comprises of fluorine-lean aromatic hydrocarbon block, and also it is ionically cross-linked with OPBI. So first, I would like to focus on the PPIM, so the phosphonated polymer of intrinsic microporosity when it's used as a catalyst layer binder. So we used different ionomer to carbon ratios in the catalyst layer when we fabricated them, and we compared it to commercial Nafion D521 with an ionomer to carbon ratio of 0.8. We see here the polarization curves for the different ionomer to carbon ratios, and we see a systematic decrease in the performance as we increase the ionomer to carbon ratio. So the best performance we obtained at ionomer to carbon ratio of 0.2. We also compared the oxygen diffusivity of these materials with Nafion, and we see that at high relative humidity, at the lowest ionomer to carbon ratio, the new materials can surpass the oxygen diffusivity of the commercial Nafion. We also estimated the electrochemically active surface area, the Stoffel slope, and the catalyst layer resistance, and also compared it to Nafion. And again, at the lowest ionomer to carbon ratio, we could have comparable performance to the Nafion-based material. Yes, so these phosphonated materials are promising to replace PFAS, and we identified as the next step in material optimization to replace the phosphonic acid group with sulfonic acid group, and we expect the materials to have higher proton conductivity, which will translate to better in-device performance. Another highlight is regarding the fluorine-lean polymers, aromatic hydrocarbon polymers that we used with OPBI as a blend, and then fabricated membrane electrode assemblies and tested them in the single proton exchange membrane fuel cell. Compare the performance with commercial Nafion 212 membrane, which is 50 micron thick and has a comparable thickness to these materials that we tested. So we see here the performance, fuel cell performance at hydrogen oxygen and under hydrogen air operation. And we see that the new materials have slightly worse performance than the Nafion, but nonetheless the performance is good. We also identified or measured different metrics, so such as the electrochemically active surface area, high hydrogen permeability, and also high frequency resistance of the materials. And currently, long-term durability tests are ongoing. I note here, unfortunately, I cannot show these results because they are still ongoing, but we are very happy to report that in the durability tests, we can match and outperform the Nafion commercial material. Besides focusing on material development, the SUSTAINCELL project also performs round-robin testing campaigns, specifically for anion exchange membrane electrolyzers and proton exchange membrane fuel cells. So we have 6 partners in the consortium at large European research institutes and universities who are performing harmonized single-cell testing using the same cell hardware with the same active cell area, and using commercial cell components and also components developed within the project. For example, we use the same harmonized testing protocols to characterize the materials, for example, by reporting the polarization curve, performing EIS measurements, also measuring the pressure distribution across the cell. So here are some preliminary results here to show the results on the same material between different laboratories, so different partners. And we aim to publish the results already this year on the AEM electrolyzers, and on PEM fuel cells we target a publication next year. Yes, we hope that these round-robin testing will present opportunities for the community to improve consistency and also build trust in uniform testing. And as my last slide, I would like to show some highlights from the project. So as for all projects, we have regular meetings. We already had 6 physical meetings, so some of the photos are shown here. We completed financial reporting, quality control, risk management, and then annual reporting to the Clean Hydrogen Joint Undertaking. And of course, we are continuously monitoring that we adhere and reach the key performance indicators indicated in the project. And with that, I would like to thank you very much for your kind attention, and I'm happy to take any question that you may have.
Thank you, Dr. Nemet. And is there any question from audience online or here? Okay, there is a question from Dr. Martinez.
Yes, thank you very much for your presentation. Very interesting, a lot of results, so congratulations. My question, I don't know if you are the person that I should address, but okay. The thing is, the slide you mentioned about the electrospinning and the oxide compounds for the solid oxide high temperature electrolyzer fuel cell, I don't remember. Here, exactly. This one, do you know the yield after the thermal treatment of this precursor after the electrospinning?
Yes, so I myself, I focus on low temperature applications. So please send us an email and then I can forward it to the coordinator, because the group of the coordinator at SINTEF is performing the high temperature studies.
Thank you. Thank you very much. Okay, thank you.
Okay. Is there any other comment, feedback? Otherwise, I think we are in time, and let's thank again Dr. Nemet. And we can move on with the 4th project of today, EMELIA. It will be presented by Dr. Frédéric Foda-Onana, and he is a research engineering at CEA, the French Alternative Energies and Atomic Energy Commission. His focus is on materials and testing protocols for low temperature water electrolysis, and his expertise covers electrochemistry and electrocatalysis. Please, Dr. Foda-Onana.
Yes, I just share my screen.
Yes. Second.
So could you tell me when you see my screen?
Yes, we are seeing it. Maybe the wrong screen, the one with the slides, the future slides. Yeah.
Is it better in this way? Sorry, like this.
Yes, perfect.
Okay. So yes, thank you for the introduction. So I'm coordinator of AEMELIA project. So the project started in January 2024. It's a 3 years project with a budget of about 2 million euros. And that project, there is 10 partners. And yes, now we are roughly at the halfway through the project. So we have a consortium among different partner, industry, and research and technology organization. So you can see on that picture, I mean, the different partner of the project. So some in Tecnalia in Spain. So I will not go through all of them. So I will probably give more details in the next slides. So yeah, the main objective for AEMELIA project is to demonstrate a 5-cell stack with 1 square centimeters for the active area, able to deliver 1.72 volt at 1.5 amps per square centimeters in diluted KWH solution and 80 degree and 50 bars. So this is quite ambitious target, and to be able to reach those targets, the idea is basically to increase the temperature and also try to reduce the membrane thickness and avoid any PGM catalyst in the electrode, and also remove the fluorine from through the membrane. And since we also want to reduce the KWH solution, so again we allow us to perform the test at higher temperature. To be able to reach this ambitious value, so we try to quantify the gain at each step from the state of the art to the final objective. So the state of the art for us is 1.9 volt at 1.5 amps per square centimeters. And so we quantify that if we increase the conductivity with 43% in conductivity, we can decrease the voltage at 1.826 volts. So we have basically 90 millivolt of voltage reduction that leads to 3.9% of increasing in efficiency. Also, we thought, for example, that if we increase the temperature, so maybe I can use the pointer. Maybe you see my mouse here?
Yeah, we can see the mouse. Yes.
Okay. So I think if we increase the temperature from 50 degrees to 80 degrees, so 30 degree increase in temperature, so we can also see that we reduce the voltage, and this leads to an increase of efficiency for 1.3%. So by adding all the test, I mean, by increasing the conductivity, reducing the membrane thickness, increasing the temperature, so we could end up with an increase of efficiency of 1.86%. So that will lead us to a voltage of 1.725 volts. This is a bit lower voltage than the target for 2030 from the SUSTAINCELL target. So this is the ambition of the project. And now I'm going to describe a bit more how what is the work plan of the project. So the project is shared in 7 work packages. So 3 of them are non-technicals for the management, communication, and sustainability assessment. And for the 4 other work packages are technical work package. 1 dedicated to the polymers development, so ionomer and membrane. Another 1 dedicated to the catalyst and electrode development. And then another about the cell and stack design, and the last for the electrochemical testing at single cell and stack level. So let's start with some, let's say, key achievement for each work package. So this work package 2 dedicated to the ionomer. So we have developed an fluoride-free membrane with the joint work between ScienceCo and the CNR in Italy. And they end up with a polymer able to reach more than 1 millisiemens per centimeters at 80 degrees, as you can see here with the red line. So which is much higher than the target of the project, that was 100 Siemens per centimeter. So with that membrane, we are able to reach one of the milestones of the project. Then we also try to use a deep learning approach to find out the best sustainable solvent to dissolve the polymer. And from that, we start with naphtha-ion because there are much more data to be able to train the model. And here you can see kind of the result between the experimental and that model can provide. And we see a quite nice consistency between the model and the experiment. And so now we will be ready to use the model with the anion exchange membrane or anion exchange polymer to dissolve the polymer. Also concerning the membrane, so we need to reduce the gas permeation through the membrane. So we start to play with fumatic or fermion polymer and to insert some catalyst inside of the membrane. So this work was performed by TNR in Italy, and they show that they successfully insert catalyst inside of the membrane with a size large enough to be integrated in the stack. Again, the stack size is 100 square centimeters. So for such kind of active area, CNR is able to introduce catalyst inside of the membrane at such large membrane size. Then now, going on work package 3 about catalyst and electrode. This work was performed at Imperial College London. The idea is to find materials able to recombine hydrogen and oxygen inside of the membrane, which is not PGM, so PGM-free recombination catalyst. And the figure of merit to find this catalyst is based on getting a catalyst able to reduce the oxygen and also oxidize the hydrogen. So they define two kind of recombination catalysts, 1 and 2. And basically with the recombination catalyst 2, we can see that we could have a good activity for oxygen reduction reaction and also for oxygen evolution reaction. So in red here, you can see the reference to the platinum. And also a very interesting figure is also this catalyst is also able to not produce a lot of hydrogen peroxide when we measure the oxygen reduction reaction. So one of the, let's say, good alternative to platinum could be this material as a combination catalyst. Again, in terms of electrodes, so we have the idea that preparing ionomer-free electrode may be really benefit for anion exchange membrane water electrolysis because you may have more open area for the fluid distribution, either for the KOH or for the gas removal. And for that, ionomer-free electrodes was prepared at INTEF with electrospin, so electrospinning of nickel nanofibers. You can see some pictures here on the left side of the slide. And also nickel iron oxide electrode deposition on the fibers, on stainless steel fibers. And so you can see how the fibers are coated with nickel iron oxide. So this is, let's say, the most innovative route to prepare electrode. But in the meantime, we also intend to prepare, let's say, more conventional electrode. And for that, we prepare also some catalysts, so nanoparticle catalysts. And for that, some group at CNRS in Montpellier, EC2MP, have prepared a catalyst for hydrogen evolution reaction. And so you can see here two kind of generation of catalysts. With the generation 2 giving much larger performance with about minus 200 millivolt as over potential at 10 million square centimeters. And also at CA, we develop a nickel iron oxide co-precipitation catalyst. And we could see that the heat treatment during the calcination process has a huge impact on the activity of the catalyst. Also, in the meantime, we also in the work package for perform some work on the design of the frame to supply the active area of the electrolyte, and fluid dynamics calculation performed at SINTEF shown that there is a, let's say, an optimal frame design where the target is try to decrease as much as possible the pressure, the differential pressure in the active area here where the reaction takes place. And so with this design here, they found out that that design is able to that design here is able to give the lower value of pressure drop in the active area. And also if how to say, the porous transport layer is thicker, so we can see a decrease of the pressure drop in the active area. Then beside of this, to get some component to start to make the stack is also ongoing. Then, as I said before, we target to perform the test at high temperature. And what it could be interesting to see here, it's different tests at different temperature was performed with two common reference membrane, the FOMATEC membrane and piper-ion membrane. And that can be seen, it's at low temperature, let's say below 70 degrees, the piper-ion membrane is performing better. But once the temperature is increased above 70 degrees, so 80 and 90 degrees, the FOMATEC membrane is performing better. So there is maybe some information to get from the structure of the FOMATEC membrane to be able to sustain the activity of the electrode and the membrane, more specifically at high temperature, to prevent any degradation of the membrane of the side chain when the temperature will be increased. Also, another, let's say, innovative condition that we want to address in the project is the power supply on the cell. So Tecnalia has defined that the pulse signal may reduce mass transport limitation when we perform some tests during the anion exchange membrane electrolysis. And they perform some tests with different duty cycle, and they found out that when we reduce the duty cycle, the current density could be much higher. So that means higher hydrogen production. But in the meantime, if we want to have the same amount of hydrogen in between these three experiment, so we will have to increase a bit more the time. So there is a trade-off to find out in between have enough hydrogen production and also not to increase too much the time. And then also in the project, we want to address the LCA assessment. So in Work Package 6, leading by ScienceCo, they find out a methodology to assess the footprint impact of different kind of membrane. And with this kind of methods, they found out, let's say, 16 category to evaluate the impact of the ion membrane. And so this method will be also used when the final membrane of AEMELIA will be defined. And so all the information regarding the project are gathered in this website. So please feel free to visit us on the web page. And so the main message I want to give you, so AEMELIA intends to reach a high performance ionization membrane reactor electrolysis with about 1.72 volt at 1 amp per square centimeters in diluted KOH solution and high temperature. So to get these KPIs, so the idea is to use fluoride-free ionization membrane and with more than 100 millisiemens per centimeter as ionic conductivity. And also all the electrodes will be hopefully without ionomer, and electrospinning and electrodeposition are the main techniques that would be used to get those electrodes. Also, we intend to remove all the PGM either from the electrode and also in the recombination catalyst. And now we have, let's say, an alternative to platinum to be replaced, to replace the platinum. And stack design and frame design are now completed based on the fluid dynamics calculation. And we have also a method to evaluate the footprint of the membrane, and that method evaluates the 16 category of the membrane. So we hope to have a high performance by increasing the temperature, and for that we need to better understand based on the comparison between Piperion and the Fomatec, why a Fomatec membrane is able to sustain high temperature while Piperion cannot. So now we are starting the second part of the project, which is mainly on electrochemical testing with the components that was developed during the first half of the project. So I want to thank all the collaborators, all the partners in the project. They are all written on this slide, and thank you for your attention. Also, I want to acknowledge the European Union for the funding. If you have any question, please pay to ask me. I will be delighted to answer you. Thank you.
Thank you, Dr. Onana. And is there any question? If not, it was a very great presentation, and let's thank again Dr. Onana, and we can move on with our last speaker of today, Dr. Donato Zangani, who will present the project Everywh2ere. And Dr. Zangani is the Global R&D Director of RINA, a leading engineering, consulting, and certification company from Italy, counting more than 6,000 people of personnel distributed in 200 offices worldwide. Dr. Zangani is in charge of the supervision of the R&D projects carried out within the RINA group and supports the monitoring and exploitation of the key exploitable results from such projects, including Everywh2ere, which was coordinated by RINA from 2018 to the end of 2023. Please, Dr. Zangani.
Thank you very much. Can you hear me and see my slides?
Yes.
Excellent. Yes. So thank you for the invitation. Happy to present Everywh2ere. Everywh2ere is, you can see here, it was started in February 2018, and we ended in 2020. I mean, at the end of 2023. So a long project, also because we had the COVID crisis in the middle, so we had to struggle about these difficult times. But anyway, we were able to continue with the project. So the goal of this project was to find alternatives to temporary diesel gensets that are used everywhere in the cities, during fairs, public events, construction sites, concerts, to power these temporary events. Also, and let's say these diesel gensets are the technology used nowadays, and we have a lot of problems with that related in particular with noise, if you like, and also emission of fine particle pollution. The idea was therefore to find alternative using hydrogen fuel cells that offered a number of advantages. So the goal of the project was to demonstrate up to TRL 8 easy to transport, let's say plug and play, as we say, fuel cell genset powered by hydrogen. And one of the let's say goal of the project was also to give a number of demonstrations around Europe of those gensets. Here the consortium that we put together in order, as you see, there is a combination of industrial partners for, I mean, market-driven design, integration, research organization for the, I mean, for the technical validation and innovation, also associations for dissemination. Rina from Italy was the coordinator. So we managed the project, and we were also in charge of the specifications for the genset. The